But it's it's a bit like this, you see, that it's wide.
Oh, that's okay.
So you could see a little bit, and then whatever was happening out over there, you had no idea. The middle was full, but who knows? You ready? Great. So, perhaps slightly perversely, let's do case 3 first. This was a case in which the modulus of the charge was greater than m. And so if you look at the metric looks like, well, exactly as it does before, minus into 1 minus 2m over r plus q squared over r squared dt squared plus the same thing to the minus 1 plus q squared if mod q is greater than m, then this function does not have a zero, real zero. Which means that it's positive all the way down to the singularity. And r equals 0 is, of course, still singular. So there are no horizons. The coordinates do not break down anywhere except at r equals 0. There are no coordinate transformations you could possibly make to get rid of the singularity at r equals 0. And so it's very easy to draw the Penrose diagram for this situation. It is, roughly speaking, the same as flat space, with one exception. There is, of course, a great deal of curvature at the origin, and that's the only real difference between this and flat space. So the origin, r equals 0, is a curvature singularity. So the Penrose diagram looks like that. This is a classic example of what is usually called a naked singularity. The singularity is not hidden by an event horizon. Furthermore, if you were an astronomer sitting at Scry Plus, up here, the singularity lies in your past light cone and in a region which you can quite happily probe. Now, it is true that there were singularities in the past light cone of Scry in our previous examples of the Schwarzschild metric and the Reissner-nordstrom metric, but that was a little bit different because there they were actually inside horizons, and you might have the feeling that somehow in a realistic model you wouldn't actually see them. Here there is no question. The singularity is not behind any horizon. It lies in the past light cone of Scry. Another problem is, of course, that you can get quite close to it. So, for example, you could imagine a causal curve that looks like this. You could orbit it, go and inspect it, and then come out, look something like that. So you can more or less directly probe the singularity. So you might ask, well, what's really wrong with this? After all, a singularity just looks like presumably some kind of lump. Quantum mechanics will manage to cure your problems with this, if you're lucky. So why is it that one gets so worried about naked singularities? So what I'm going to tell you is sort of qualitative. You can do some complicated mathematics and convince yourself that it's really right. But here's a qualitative explanation as to what's wrong. Suppose, for example, I construct a space-like surface in this space-time. Let's call this sigma. The whole point of physics, that spans the entirety of the space-time, so it represents a surface of t equals constant. The whole point of physics is, or at least at some level, given the initial, at least classical physics this is true, given the initial conditions on this surface, so if I specify something like fields and first derivatives, then I should be able to calculate the behavior of everything to the future of this surface. So if you specify fields and derivatives on sigma, first time derivatives, you should be able to predict the future. Now, suppose you were doing Minkowski space, you know that's sort of true. The Penrose diagram of Minkowski space looks something like this. Nothing peculiar happening there. You have a surface here, and you ask what happens in the future. Let's say, for example, here. So let's call this one sigma minus and this one sigma plus. Then, of course, given what happens here, you can calculate what happens there. And there isn't really a problem with that. Let's contemplate the problem in this space-time. To calculate what happens here, you need to, well, you can measure what happens here, you need to calculate what happens here. But the problem is that if you took this point, say, and you looked at its past light cone, the past light cone of this point looks something like this, and it will intersect the singularity. That means that in order to be able to predict what happens at this point, you need to have some knowledge of what happens at the singularity. But by its very nature, you have no idea what happens at the singularity. That's because everything blows up, and you cannot control any of the information that has anything to do with what happens on this surface. The only way in which you're going to be able to make any sensible prediction about what happens on this surface would be to construct a little time-like tube around this surface, so it looks something like that, and specify boundary conditions on it. If you specify boundary conditions on that surface here, then of course you can calculate what happens here. So the first thing is that you would need to be able to specify boundary conditions on this surface. Let's call this surface T. T for time-like tube. You could, for example, say that phi was equal to 0 there, if phi was the field you're interested in. But the real trouble is that because you really want to be able to contract this thing down to 0 size, otherwise things can happen inside it. And if you do that, you see what will happen is that the whole thing becomes singular. And effectively it means that you do not know what to do. So you would need to specify boundary conditions at the singularity. In other words, you really need to know the physics of the singularity. So you'd need to be able to know enough about singularities or whatever replaces them in quantum theory to provide these boundary conditions. And of course one has not the faintest idea. It's widely believed that this kind of singularity, these naked singularities, do not actually happen in realistic gravitational collapse. I choose my words carefully because you can invent models in which you have non-realistic gravitational collapse, and they do occur. But typically that involves systems without pressure. That doesn't seem very physically realistic, certainly not for anything that involves fermions. So perhaps one of the most important unsolved conjectures in general relativity is called the so-called cosmic censorship conjecture. Which asserts that this kind of naked singularity does not happen. That may seem very loose for a conjecture. It is not well posed as it stands. It's a few words without precise meaning. And the reason it has no precise meaning is because nobody is really quite sure of how you should formulate the cosmic censorship conjecture. So I have deliberately left it in a rather loose and ill-defined fashion. Cynics would say that means that the cosmic censorship conjecture tells you whatever you would like it to tell you when you manage to prove it, which is true. But the basic feeling is that there's something unacceptable about this kind of behavior. Let me add one thing parenthetically to this, and the same kind of behavior can happen in the Schwarzschild metric. It has a similar problem. If you go back to the Schwarzschild metric, we wrote it in the form ds squared is minus into 1 minus 2m over r, dt squared plus the same thing to the minus 1, dr squared plus r squared d omega 2 squared. And we said that m was positive. But m is just a constant of integration, so we can ask ourselves what happens if m was negative. Then what happens is that this function here has got no zeros down to r equals 0, and you'll end up with the same kind of situation. The Penrose diagram for this situation corresponds to a naked singularity at the origin. This almost certainly does not happen. Whilst it's true that m is a constant of integration and can therefore be anything you like, to have m negative would require you to have negative energy, and there is no evidence that negative energy really exists. There's certainly no example of negative gravitating mass. So this is almost certainly ruled out. No negative gravitational mass is known. Furthermore, if it were known, it would almost certainly lead to some horrific instability, for the very simple reason that if you could have negative energy, there is no reason why that negative energy should be bounded below by anything. So you could always get more energy out of the system by simply extracting more positive energy and giving you something which is more negative. So this is kind of indicates, if it were possible, it would indicate an instability. So, for example, you could take Minkowski space and ask, is that the thing that has minimum energy? If the answer is yes, then Minkowski space is stable, which appears to be a fact. If it is not the minimum of energy, you could imagine a process in which it decays to something that was the minimum of energy, and that would have to have negative energy, and it would correspond to something like this. I think we are pretty certain that does not happen, although it's hard to rule out completely. So this kind of thing is generally regarded as pathological. I will provide a proof that energies have to be positive under certain circumstances later in the course.
Why doesn't the case 1 suffer from probably naked singularity? Because we have this piece.
It does, but it's kind of different. Let's draw a picture. So we're asking a question about gravitational collapse, really. So let's suppose let's look at the Penrose diagram we had. This is always harder to draw than you ever imagine. It's easier to draw it in bits rather than all at once. That's probably enough. Suppose that we sat here and we said we are not going to allow singularities in the past. So we start from a perfectly regular universe in which there are no singularities, but there is charged matter. So we know that we've defined away that bit of the metric, and we ask about gravitational collapse. So you can imagine you have some material here which is undergoing gravitational collapse, and it's got mass less than q, so we don't have a naked singularity problem. What would you actually get? Well, the stuff would collapse into the singularity, and presumably it would look something like this. So this is a collapsing body. So you wouldn't have this region. But after a little bit of time, it would all settle down to something which is time independent. So to the future, it would look something like this. That may seem a little bit fanciful, but this is the Penrose diagram you get from gravitational collapse. So this is a collapsing body. I'll say more about gravitational collapse later. But presumably the whole thing settles down to something static in the future, so it looks something like that. So now the question is, why don't you see a singularity in the past? If you are in this region, then you look along your past light cone and you don't see a singularity. If you go to the future, up here, this is as far as you can go if you're out at infinity. You get as far as this, and so that corresponds to your horizon, but there is no singularity in your past light cone. The only way in which you're going to see something singular is if you are brave enough to fall in through the horizon along a curve that looks like this, and then you will certainly see something if you did that. Then you could have a singularity in your past light cone. But this observer does not count. This is not an asymptotic observer. So if you restrict yourself to this region here, there really is not a problem of singularities as far as you're concerned. So that's the basic difference between a naked singularity and a singularity caused by gravitational collapse. It does not sit in your past light cone in a realistic, or at least quasi-realistic model.
But you could have an observer in the other scribe class.
Oh, up here? Oh, yes. Perhaps. I would like to treat that particular case much later in the course, because you might be able to convince yourself that that too is not very realistic, but we haven't done enough to do that yet. The reason for that is, I don't want to go into it now. If there is time, I will return to that particular point. The real trouble with the Reissner-nordstrom metric and its generalization, the Kerr metric, is that whilst it's true that you have all these extended regions, they've really come about because you've assumed that everything is precisely static. And it's not clear that that's really true in any realistic thing, but it is certainly true for the models that you can construct explicit metrics for. By explicit, I mean not numerical. For numerical things, of course, you don't really quite know what's going on when you try to do global calculations of this type. So, I guess that's half an answer. Well, 2/3 of an answer. The problem is, of course, that nobody has managed to prove that this is actually what happens. That's because it would all require, well, you can do it under assumptions of symmetry. If you drop the symmetry assumptions, it's kind of hard to do, and I don't think the numerical techniques are really up to it.
Is it okay just to think of this as saying that static charged black holes, static charged black holes don't exist? So they existed for eternity, then you could probe them. But the reason why we can't probe is because they don't actually not static.
Classically, that probably isn't true. There doesn't seem to be any classical reason why you can't have a charged black hole. Yeah. There's a quantum mechanical reason why you can't have one, but we'll come to that later. That may be much more important because, but actually, even that isn't really true. So case 2 is a counterexample to that. So, having said that case 2 is a counterexample to that, let's move on to case 2. Case 2 is a very, very special case. This was the modulus of Q is equal to M. Under those circumstances, the best thing to do is to write the metric explicitly in the following form. That emphasizes the fact that this function here is positive or 0, and it has a double zero at r equals m. Nevertheless, at r equals m, this metric is singular because there is a coordinate singularity. So we need to get rid of this coordinate singularity. We already have a technique which works. We just have to do some horrible integral. We can do exactly the same thing as we did before and invent a set of null coordinates. So invent null coordinates. These represent radially outgoing or ingoing light rays, so they correspond to u or v, theta and phi constant, where u or v are advanced or retarded or advanced time coordinates, so that v, I will say, is t plus some function of r, u is t minus some function of r, and you adjust the function of r to give you something nice. We do that exactly the same way that we did it before. So every time you see dt, you can write du plus f prime of r dr. And if you substitute that into the metric, you will get ds squared. Let's call this function v of r for the time being. Minus v of r dt squared, so that's du squared, minus 2v f prime du dr plus dr squared into 1 over v minus f prime squared times v plus r squared d omega squared. So again, as before, the choice v equals 1 over f will give you something nice. Under those circumstances, the metric is just ds squared is minus v of r du squared minus 2 du dr plus r squared d omega 2 squared. And that's the same form of the metric as we had before. You might or might not need to know the explicit coordinate transformation. Obviously, that coordinate transformation has got to be singular. And if you do the calculation, you will discover that. Well, from here, df dr is equal to 1 over v, so that's r squared over r minus m all squared. So f is equal to the integral of r squared dr divided by r minus m squared. And you can entertain yourself by doing this. And I got r plus 2m times logarithm of the modulus of r minus m squared over r minus m. So this coordinate transformation is indeed singular at r equals m, more so than was the case in the other examples. The logarithmic singularity is familiar, but there is a pole as well. However, we should expect that because you will not get rid of a coordinate singularity except by a singular coordinate transformation. Now we can just happily construct the Penrose diagram for this situation. Similarly, you can do the same kind of thing for v. There is an asymptotic, I'll warn you again that this diagram is infinite in the vertical direction going both ways. So, there is the original region that you started off with in which the coordinates at the top left-hand corner work. If I construct lines of constant u, they of course look like this, they're constant retarded time, and they can go through this surface r equals m quite happily. And if I have done this right, let's see, if r tends to m from above, this expression is becoming infinitely negative. So that means that this thing is infinitely positive, which means finite u, as r goes to m, t becomes infinitely negative. So this surface down here corresponds to t equals minus infinity. Now, as you go through this surface, what you thought of as lines of constant t and constant r, and you'll have to remind me which way round was which, because I can't remember.
Constant t green.
Constant t was green, okay. So your lines of constant t look something like this. The t coordinate breaks down on that surface, but inside this region you can still have t and r and theta and phi, and it all works perfectly. The only advantage of having the u, r, theta, phi coordinates is you can go from one region to the other. But unlike what happened before, surfaces of constant t remain space-like when you go inside because v does not change sign, it's got a double zero. So inside, surfaces of constant t look like this. You can decrease r down to the value of 0, where there is obviously a curvature singularity, and so you get a picture that looks like that. Similarly, you could have extended to the future. And if you had done that, you'd have used v r theta phi coordinates and gone this way, and you will find a region again that is singular at r equals 0, and lines of constant t look something like that. So that's quite different to what happened in the previous case. If you drew lines of constant r in this, well, they look something like this here, and then like that in this region. Now, of course, you can now declare that something is missing. So if you sat in this region, you would notice that it was isometric to this region, and so to the future of this, you'd find another region that looks like that. Similarly, since this region is isometric to that one to the past, there must be another region that looks like this, and these are another asymptotically flat regions. Then since this is isometric to that, then there must be another one to the past, etc. forever. And then similarly to the future. And so forth. Now, the next thing that you might attempt to worry about is what happens if you start off in one of these regions and attempt to move in a space-like fashion, decreasing r. So you would move in, say, that direction. What would actually happen to you? So you're going to move at constant finite t in the to decrease r. If we did this in the Schwarzschild metric or the Reissner-nordstrom metric with m greater than the modulus of q, we would discover some more asymptotic regions. And to get over the singularities that we find, we would have to invent the Kruskal transformation. However, in this particular case, life is a bit different. We can forget about this term. This is just two spheres of constant r. That's not going to do anything interesting to us. So let's fix t. Put theta equal to pi by 2, so we're just in the equatorial plane, and look at the r phi form of the metric. That encompasses enough information for us to figure out what's going on. The resultant metric is a two-dimensional metric that is cylindrically symmetric and looks like that. Now, you can justifiably say, well, if r tends to m, this of course blows up, and something bad happens. Of course, that's a coordinate singularity. So I want to invent a new coordinate, which I will call lambda, and it's going to be, d lambda is going to be r dr over r minus m. If I make that coordinate transformation, then I can look again at what happens as r goes to m. So, lambda is the integral of r dr over r minus m, which is the same thing as r plus m times the logarithm of the modulus of r minus m. So you will see, of course, that diverges as r goes to m in some rather unpleasant way, but ds2 squared is equal to d lambda squared. Now, as r tends to m, this term here is just going to tend to m squared and is finite. So it's m squared times 1 plus small correction times d phi squared. That is the metric on a cylinder. So you can draw a picture of what this geometry looks like. You know that if r is large, then this thing is going to sort of start increasing, like r. So what you will see is a sort of trumpet type thing. But as r tends to m, then the radius of your cylinder and it goes on forever, tends to just m. Lambda goes in that direction, increases there, and out here, basically, the radius of the cylinder is tending to r. So here the radius is tending to r. Here the radius tends to m. Lambda increases in that direction, and of course decreases forever in that direction, and never stops. So what this tells you is that if you go in a space-like direction, decreasing r, you will end up in an infinitely long cylindrical region, which is usually called an internal infinity. So for r tending to m, one finds an infinitely long Now, if at constant t, this is of course an infinitely long cylinder of topology r cross S2. Here I drew it as topology having r cross S1 because I can't draw three-dimensional cylinders on a two-dimensional board. So if you go in this direction, you can keep going in a space-like direction at any value of t that's finite forever. So these points here represent internal infinities. If you like, I'm not sure you should like, but if you like, you can regard this as a kind of limiting procedure of what happens in the Reissner-nordstrom solution with m greater than q. If m is greater than q, then there is a sort of wormhole, a space-like wormhole that joins the two asymptotically flat regions. What's happened, as you have taken the limit as m tends to q, you have essentially stretched this wormhole out to become infinitely long and separated the two bits. So this kind of thing, well, is what you get. Now, so that's the first very peculiar property of this metric. The second very peculiar property of this metric is that it admits the most astonishing generalization. I have constructed here one black hole sitting in space. Typically, you can't have more than one black hole, because if you did, and m was not equal to q, then you'd have Newtonian gravitational attractive forces between the masses. And if you had charges, it's true that if the charges were the same sign, it would be repulsive. But if m is greater than q, the Newtonian attraction will always outweigh the electrostatic repulsion, and you'd never find any static solution with more than one black hole in it. Now, it is intuitively obvious that if m is equal to q, there is the possibility that you could have a static balance between the two. The gravitational attraction of the masses would exactly balance the electrostatic repulsion of the charges. And therefore, you could have any number of black holes you liked. You might think this was completely crazy because the Einstein equations are hopelessly nonlinear and such a thing seems to be fanciful. Amazingly, you can do it. And you can see how to do it. The easiest way to do it is to start from this form of the metric. This form of the metric has got a very special point in it, namely either r equals 0 or r equals m, depending on your point of view. So the simplest thing to do is to try and make space look as much like space as you possibly can. So step 1 is to rewrite the metric in what is misleadingly called a conformally flat form. I think I should really call it spatially conformally flat, but it never is. So I want to start off with a metric which looks like ds squared is minus u squared dt squared. So I'm going to write it as explicitly as u squared, where u is equal to 1 minus m over r, plus dr squared over u squared, plus r squared d omega 2 squared, and something which is explicitly conformally flat spatially is going to look exactly the same as this, but you would like to redefine the radial coordinate so that you end up with something which looks like this in space. And then whatever you get there comes along for the ride. The point about that is that this is the metric on three-dimensional flat space. You can always do that for spherically symmetric metrics. If you try to do it for Schwarzschild, you'll discover it's a horrible mess. So, to make that work, you've got to put dr over u equal to phi d rho, and you have got to put r equal to phi rho. So the simple thing to do is to eliminate phi from these equations because you have no idea what phi is. So you divide this by this, and you will get dr over ur is equal to d rho over rho. So that tells you that integrating it up gives you this. So that tells you that log rho is the integral of dr over ur. But u is equal to, we didn't write it down, u is r minus m over r. So ur is just r minus m. So this is the logarithm of r minus m, I'm going to take the positive, plus a constant. You may as well choose the constant to be 0, so you want to make the substitution rho is equal to r minus m, which is very trivial. What is phi? Well, phi is r over rho. R over rho is m plus rho over rho. So this is equal to 1 plus m over rho. So the new form of the metric is ds squared is equal to phi squared, well that's 1 plus m over rho all squared into d rho squared plus rho squared d omega 2 squared. And then you have the minus dt squared Well, since you know that u was r minus m over r, in terms of rho, it becomes rho. This is rho over rho plus m. So this is just 1 plus m over rho to the minus 2. So that's a new form of the metric. Rho equals 0 is r equals m, which is where the horizon is. It looks singular. We should not be surprised by that, but we should also not be alarmed by it. It's true that it's a coordinate singularity, but it is a horizon, and you know how to get rid of the coordinate singularities at the horizon, and therefore it does not pose a problem for us. But this is only a coordinate singularity. Still, rho equals 0 looks special, and we don't like that. So, the next step is to construct Cartesian coordinates on this R3. If you do that, you'll end up with a metric that looks like ds squared is minus into 1 plus m over, well, I suppose I would call rho the modulus of x. Let's call this x is x, y, z to the minus 2 plus 1 plus m over mod x to the plus 2, we're missing dt squared, into dx squared plus dy squared plus dz squared. So that corresponds to a black hole at the origin. So that is an alternative form of the metric where I've written it in as flat space-time form as possible. It is still the case that this single black hole is at the origin, so I'd like to move it. So I'm going to move it to the point x, 0. Then what will happen is that ds squared is equal to minus into 1 plus m over the modulus of x minus x0 to the minus 2 dt squared plus 1 plus m over the modulus of x minus x0 to plus 2 into dx squared plus dy squared plus dz squared. So now we have a black hole at x0. These are vectors. I think we have to stop there for today.
But isn't it the horizon to that x0 and not the black hole?
What's the difference?
Oh.
The horizon is all I would typically mean by the black hole. I can't finish this calculation today, I know that.